Hi students, so this week we're going to dive more into examples of dynamic programming. We're going to do two particular interesting cases where we can get a fast algorithm and solve an interesting problem using DP, dynamic programming. So these two examples are the longest increasing subsequence and the longest common subsequence between two sequences. So I'll explain what those are in a little bit. I'm actually going to hand off a lot of the explanations to Professor Eric Vagoda, who's also faculty at Georgia Tech, to do these explanations because he already has some actually great videos on this. But before I do that, I just want to hand it off to my colleague, Professor Crape, because he actually wants to do a dance number for the students. So I'm going to give it to him. So take it away, Professor Crape.
Excuse me? What was that? You would like me to do a dance number for the students? Are you crazy? I would never do a dance number for students.
Okay, before I send you off to watch Professor Vagoda's lectures on the longest increasing subsequence, which is today's lecture, I just want to remind folks that the difficult and interesting thing about dynamic programming solutions is that what you have to do is break the problem up, which is some big problem, let's say of length n, into solving some smaller instances of the problem. We call them subproblems. So to solve the ith iteration of the subproblem, somehow you can recurse to smaller iterations of the subproblem. Maybe, for example, in terms of, you can solve L of I, you may have to reduce that to L of I minus 1. But there are other things. You may be able to recurse deeper into the sequence. The hard part, though, is coming up with what are the subproblems. Typically, the first thing you try, the first way you break the problem up into subproblems is not the correct one. The intuitive, natural thing you would try isn't going to work. You're going to see Professor Vagoda explain that. Let me just emphasize that with the case of the lane-changing example that I described in the last lecture, what I mean by that. So let's just go through that example. So you guys remember this problem before? We had the optimal way of changing lanes. I think it was Peter Gibbon who's looking to change lanes and get through traffic as fast as possible. If you knew the speeds of the various segments, let's say you have these various nodes in the highway, and you knew the speed it took to get from node to successive node, what would be the optimal sequence of lane changes to take to get from the start to the end? We broke this problem down into a sequence of subproblems, and we solved those subproblems in green. If you remember, I wrote down, I computed these distances in green. What were those values? What were those numbers? Like, for example, here we have the number 29. What was that number? If you recall, what we were computing there was the shortest path to begin at the start node and end at this particular node, right? So the green number 4 here, we arrived at 4 for this first node on the right. We arrived at 4 because the shortest path from the start node to that node, there's actually only one path we can take. It's through this bottom edge. That's a distance of 4 because it takes 4 seconds. We said what was written in red, 4 seconds to get from the beginning, the start node, to this initial node. And then we were able to recurse on that, right? Then to get from this upper right node here that has a number 19 on it, right? To get there. We asked ourselves, what was the shortest path to get there? Well, first we said if we came from this node that was marked with 15 and then paid 10, that's not as good as coming from this bottom node, which is marked 4, and then paying 15 from there, because 15 plus 4 is 19. But the key thing to note here is that we had to realize, to solve this big problem, we had to realize we could break it into these smaller subproblems. In this case, the smaller subproblem is computing the shortest distance from the start node to an intermediate node. Without having seen the solution, it might not be obvious that's the right way to solve this problem. It takes a little bit of ingenuity to come up with this correct subproblem. So when you're solving these dynamic programming problems, just keep in mind that the hard part is coming up with the correct subproblem and then figuring out how you can recursively solve them in this iterative fashion, right? How you can reduce solving one problem to smaller instances of that problem. So just keep that in mind when you're trying to design dynamic programming algorithms, that the real intelligent piece is figuring out what are the subproblems and how do you solve them iteratively. So keep that in mind for the two problems we'll be looking at next. The first is longest increasing subsequence, and the second is the longest common subsequence. I'm going to now toss it to Professor Vagoda's lecture so you can see how to solve the LIS problem now.